What really keeps a bridge standing? The hidden science behind bridges. Imagine driving across a bridge that weighs thousands of tons, carrying cars, trucks, wind, earthquakes, and yet it stands perfectly still. Have you ever wondered what actually keeps a bridge standing? Is it just concrete and steel, or is there something deeper? In this video, we will uncover the real science behind bridge stability, from forces and materials to the design principles engineers rely on every day. The basic idea: load and balance. At its core, every bridge is a system of balance. A bridge must safely transfer its own weight, known as dead load vehicles, and people, known as live load, wind, temperature changes, earthquakes, and water forces. All these forces travel from the bridge deck to the supports and finally into the ground. If this load path is broken, the bridge fails. A bridge stands because forces are controlled and guided, not just because materials are strong. The forces acting on a bridge. Every bridge deals with four main internal forces. Compression. Forces that push materials together. Concrete performs very well in compression, common in arches, piers, and columns. Tension. Forces that pull materials apart. Steel is strong in tension, seen in cables and reinforcement bars. Shear. Forces that try to slide one part of a structure over another, most critical near supports. Bending. A combination of compression and tension. The top of a beam is in compression, the bottom of a beam is in tension. A bridge remains stable when each force is resisted by the right structural element. Why bridge shape matters. The shape of a bridge controls how forces flow. Beam bridges. Straight horizontal beams. Loads mainly cause bending, used for short spans. Arch bridges. Forces flow as compression along the curve, very little bending occurs, one of the strongest bridge forms. Truss bridges. Made of triangular elements. Forces are split into tension and compression, very efficient use of material. Suspension and cable-stayed bridges. Cables carry tension, towers carry compression, used for very long spans. Engineers choose bridge shapes that allow forces to follow the most efficient path. The role of materials. Bridges do not stand because materials are strong. They stand because materials are used correctly. Concrete. Strong in compression, weak in tension. Steel. Strong in tension and compression, flexible and ductile. Reinforced concrete. Concrete resists compression, steel reinforcement resists tension. Cables. Carry only tension, used in long span bridges. Good design means matching the right material to the right force. Foundations. The invisible hero. A bridge is only as strong as the ground beneath it. Foundations. Transfer loads safely into soil or rock, prevent settlement and tilting, resist erosion and scour from water. Common foundation types. Shallow foundations, pile foundations, caissons. Many bridge failures begin below ground, not above it. Safety factors and engineering design. Bridges are designed with large safety margins. Engineers consider maximum traffic loads, extreme weather conditions, material aging and corrosion, unexpected events. A bridge designed for one load can safely carry much more. This extra strength is called the factor of safety. Why bridges fail. Most bridge failures occur due to design mistakes, foundation scour, corrosion of steel, overloading, poor maintenance. Each failure teaches engineers how to build safer bridges. Conclusion. So what really keeps a bridge standing? Controlled flow of forces, smart structural shapes, correct use of materials, strong foundations, careful engineering design. A bridge is not just concrete and steel. It is physics and engineering working together. If you enjoyed this video, like and share, subscribe to Blueprint to Reality, comment which bridge type fascinates you the most.